All right, this video is for AP Calculus, and we're going to talk about applications of derivatives in physics, which is one of the most common application word problems that you'll see on the AP exam. So there's some terminology associated with this. If the original function is a position function, so we usually will use either x or s for the function name. And the independent variable is time in these cases. So if you have a function for position versus time, in other words, you plug in a time and it tells you the position of an object, and we're moving in just one direction here, right? That if you take the derivative of that function, the result is called velocity. And the symbol specifically for that is v. So you should use v always for the velocity. For position, you should either use s or x typically, or y. Okay, so a direction, and this v is reserved for velocity. That is the derivative of the position. If you then take the derivative of the position, because the velocity is how fast the position is changing with respect to time, if we take the second derivative of position, or the derivative of the velocity, with another derivative, you get what's called acceleration, which is how fast the velocity is changing at a specific time. So you can take derivatives to go from position to velocity, and then from velocity to acceleration. And those are the three that are worked with in AP Calculus. Now, if you were to take a third derivative, there is a name for that as well. If you think about it from physics, right, there's a law, force equals mass times acceleration, one of Newton's laws, that says that accelerations are caused by forces that are acting in the same direction, typically. And that means that if the acceleration is changing, that means the force producing it is changing. Like imagine you're pulling on an object with a rope. If you want the acceleration to change, then you have to change how much you're pulling on the rope. So the third derivative, the unofficial name for it, is called jerk. It's how fast the force is that's changing that's causing the acceleration. And then physics students wanted to come up with even additional names, so they named the fourth, fifth, and sixth derivatives too. They're named Snap, Crackle, and Pop after the Rice Krispies cereal, but there's no particular use for those things. Jerk, though, has sort of a use in physics, but we restrict ourselves to just position, velocity, and acceleration with the standard symbols V for velocity, A for acceleration, and either X or X, S or X, or Y for the position or jerk. All right, now this is an important point too. We say that an object speeds up if the velocity is positive and it's increasing. So imagine that we had, this is defined as the positive s direction, so distance. And we have an object who's currently at this position, right? If the velocity is, say, 10 in the positive direction, and then later on the velocity is 15, that means, so this is the speed, the velocity, right? And that means this object is not only moving to the right, but it's speeding up, right? So when the position is positive and the velocity is positive, then we say that the object is speeding up, speeds up, right? On the other hand, if you have the velocity is in this direction, so that's, say, the velocity is 10, but then at a later time the velocity is only 5, and then the velocity is 2, then it's moving in the positive direction, but it's doing so slower and slower. So if the position sorry, I misspoke here. If the velocity is positive and the acceleration is positive, in other words, the numbers are getting bigger for velocity, then we're saying speeding it up. If the velocity is positive, so we're moving in the positive direction, but the acceleration is negative, meaning that the velocity numbers are decreasing, then we have to say that the object slows down. Okay? The same is true in the negative direction. Let's say that this is the positive direction, but I'm currently moving in this direction. So my velocity is negative 10, let's say. And then at a later time, my velocity is negative 20, and then my velocity is negative 30. If my velocity is negative and my acceleration is negative because the numbers are getting more negative, the sign is the same, then this object is speeding up. This speeds up. It's just doing so in the negative direction. And if you had a velocity that was negative 10, and then the velocity was only negative 5, that means that the velocity would be negative, but the acceleration would be positive because you're going from a negative 10 to a negative 5, which means numerically those numbers are increasing. So the derivative of velocity would be positive. And if the signs don't match, that means that the object is slowing down. Okay, so the result of all that is this. Whenever you have figured out what the functions for velocity and acceleration are, if the signs are opposite, if you have opposite signs, that means the object is slowing down. And when the signs are both positive or both negative, the object is speeding up. We'll see examples when we look at the examples. So usually these are kind of big multi-part word problems here. And let's take a look at them one at a time. And as always, you're welcome to pause the video. I'll use the same screen. I'll just keep erasing the work here. So we'll do these one at a time. All right, so first they're telling me here that a particle is moving along the x-axis. So the x-axis is the direction here. Such that its velocity at time t, where time is between 0 and 5, is given by this velocity function. Right? At time t equals 1, the position of the particle at t is 1 is 4. So if this is a 0, we are at 4 at t equals 1. So the object is right here, right now. Okay. First question, find the acceleration of the particle at any time t. Acceleration is the rate of change of velocity. So what I would show for work for this part is I would say a of t is equal to the derivative of this, which is negative 12t plus 30. Okay, so that's the answer to part A. Okay, part B says to find the minimum acceleration of the particle. Okay, so for that one, we're going to do a candidates test, right? Minimum acceleration means we're trying to find the minimum of this function over this interval. So we're going to do a candidates test. And we're going to figure out times when this may occur. And we'll automatically put the 0 and the 5 on our list, but we will also put in the critical values where the derivative of this is equal to 0 or does not exist. So let's take the derivative, a prime of t, since we're minimizing this, and that is negative 12. Is there any place where the derivative is 0? Nope, not applicable. And is there any place where the derivative does not exist? Nope. So we get no additional values. So we're just plugging these in, and we're plugging them into the acceleration function, which is negative 12t plus 30. So that means when I plug a 0 in for time here, I get 30 as the acceleration. And then if I plug a 5 in here, that's negative 12 times 5 plus 30, right, which would end up being negative 30. Okay, since we're being asked for the minimum acceleration, that's this number. So the answer to part B is the minimum acceleration is negative 30. Now that would be like meters per second in terms of units here, but they didn't tell me that. In fact, let's go back and talk about this for a second. What are the units? So the units for position are a distance unit, like meters or feet. The units for a velocity are a slope, so that's like meters per second. And then this is the rate of change of that derivative, so that would be meters per second, or sometimes written meters per second squared. Right, so since we're talking about acceleration, this should be a distance over a time squared. So this would be like negative 30 meters per second if they gave units. But if they don't give units, you don't make units up. Okay, when is the particle at rest? So the particle is at rest. I would write this for C. Particle is at rest when the velocity is 0, when v of t is equal to 0, right? And they gave me v of t equals 0, so I have to solve this equal to 0, right? Let's see if we could factor this. Can you do this? Yeah, I think we can do this. That would be negative 6t squared plus 30t minus 36 has to equal 0. We could factor out a negative 6. That would be t squared minus 5t let's see, minus would be plus 6. Right, let's just double check that. Negative 6 squared plus 30 minus 36. And then was this factor? I think so. That's going to be t is, let's see, is that factor? Let's see, multiplies, yeah, 2 and 3, right? Negative 2, negative 3. So that would be add up to negative 5 plus 6, yes. Okay. So there are 2 times when that occurs, at t equals 2 and at t equals 3. So we can go ahead. Those are both inside the interval from 0 to 5, so we have to report both of those. We'll say the particles at rest, so that we can just say which occurs at t equals 2 and t equals 3. If there were units here, it would be time units, like seconds or minutes. Okay, when is the particle moving to the left? Okay, so for that one, the particle will be moving to the left whenever the velocity is negative, right? If the velocity is less than 0, we're moving to the left. If the velocity is 0, we're at rest. And if the velocity is positive, we're moving to the right. So what I would do for answering D is I would say the particle is moving to the left when the velocity is negative, is less than 0. Now there's 2 ways we could solve this. If we have a calculator and we're allowed to use a calculator, we could graph the velocity function and find that this way. So let's do it that way. So let's see, I'm going to enter the velocity function, negative 6 variable q squared plus 30 times the variable k minus 36. And then I'm going to graph this. I'm only going to graph it over the region of interest from 0 to 5. So if I go from 0 to 5, I'll start with negative 10 to 10 here. Let's see if we see a curve. Yes, we do. Okay, so that's good. So this would be, we're moving to the left of this number and to the right of this number. And I could use my, now actually I don't need to actually figure those out because we just figured out in the part up here that is 0 specifically at 2 and 3. So it looks like the velocity, the velocity is negative between times 0 and 2, and then again from 3 to 5, because that's negative. So we could use a calculator graph. If we didn't have a calculator graph, then what we could do is this. We could say we're going to go from 0 to 5 on a number line, splits us apart at 2 and 3, and we could pick test values to plug in there. Like we could test 1, test 2.5, and test 4, and just determine the sign here. So like when we plug it, like b of 1 here, would be negative 6, so that is a negative. And then 1 minus 2 would be a negative. And then 1 minus 3 would be a negative. 3 negatives will make this less than 0. If you plug 2.5 in here, the velocity at 2.5 would be negative, times 2.5 minus 2 is positive, and then 2.5 minus 3 is negative. So that would actually be greater than 0. And then you can plug this in and find that that's less than 0. So you could do a number line test if you didn't have a calculator, if it was on a non-calculated part. But if you do have a calculator, you can just graph it and look at the graph to determine that this occurs 4. So you can say which occurs 4. You can either use interval notation or you can use this time. So t is between 0 and 2 and between 3 and 5. Okay, should we actually include the endpoints? This is a kind of a key point here. Let me make that a little nicer. Verse 4, 0 to 2 and 3 to 5. Well, let's look at the graph again real quickly. At 0, the velocity is negative, right? If I plug a 0 in here, it is negative. So I think we should include that endpoint, right? But at t equals 2, it's 0, so it's actually not negative. And the same thing is true over here. It's negative at 5, but it's 0 at 3. I think the most correct answer here is that the particle is moving left at 0, and then every time up to but not including 2. At 2, it's at rest. And then it's at rest at 3, but just on the other side, and all the way to and including 5, it is moving to the left. Okay, and then finally, the last question here is the particle speeding up or slowing down at t is 1? So to answer that question, let me write over here. Let's figure out what the velocity and acceleration are at 1. So v of 1, if I plug that in, that's going to be negative 6 plus 30 minus 36, which is going to be less than 0. And the acceleration at 1, because we had acceleration calculated here, would be negative 12 times 1 plus 30. Negative 12 plus 30 is actually going to be greater than 0. So since I have a negative velocity but a positive acceleration, that means that the particle is moving down. So I would say because v of 1 is less than 0 and acceleration of 1 is greater than 0, the particle is slowing down at t equals 1. When the signs are opposite, the particle is slowing down. When the signs are the same, the particle is speeding up. All right, so that's a good kind of comprehensive first example. Let's take a look at another example, very similar. Definitely try pausing the video and solving this first, and then unpause and see how you did. All right, so first we have got a velocity function given. At time t equals 0, the position is 0. Find the acceleration of the particle at any time t. So we will, for part A here, we will compute the derivative. So let's see, we could use product rule for that, or I can multiply it out. Let's do that. Let's multiply this out. So this is 3 times FOIL here would give me t squared minus 4t plus 3, which means this is 3t squared minus 12t plus 9, which makes the derivative 2 times 3 is 6t minus 12. All right, so that's the answer to A. Find the minimum acceleration. Minimum acceleration is a candidates test. So we're going to do a candidates test. We will find times when we might have a min, and we'll plug those into the acceleration. So we have to put the endpoints of the interval, which are 0 and 5, and then we have to add any critical points. So the derivative of this function is 6. That provides no places where this is equal to 0, and also no places where this is undefined, so there are no additional points. If I evaluate A at 0, that would be negative 12. And if I evaluate this at 5, that will be 30 minus 12, which is 18. The minimum there is, the numeric minimum is negative 12. So I'm going to state that as a little sentence here. The minimum acceleration is negative 12. And again, there's no units here, so I won't try to make some up. When is the particle at rest? That is going to be whenever the velocity is 0. I like to just state that. The particle is at rest when the velocity as a function of time is 0. So that is when 3 times t minus 1 times t minus 3 equals 0. So this occurs, which occurs at t equals 1 and t equals 3. Right. When is the particle moving to the left? So the particle is moving to the left. The particle is moving to the left where the velocity is negative. Right? Positive is to the right, negative is to the left. Oh, so when does that occur? Let's do the test value method. We could use a calculator, but let's try it this way. We know that this is at rest at 1 and at 3. So if I test some values here, like let's test 0.5, 2, and 4. So if I find the velocity at 0.5, I'm using this equation here. This is going to be a positive for the 3 using this equation. If I plug in 0.5 there, I get a negative. If I plug in 0.5 there, I get a negative. So that is greater than 0. And then let's see, the velocity at 2 would be, the 3 is positive. Plugging in a 2 there would give me a positive, but plugging in a 2 here will give me a negative. So that means that this is less than 0 here. And the velocity of 4 is everything is positive. So that's positive, positive, positive. And that is greater than 0. So since we're looking for places where the velocity is negative, that only happens in this middle interval. So we can say which occurs for t between 1 and 3. Okay, and I'm not going to put the endpoints on because the particle is at rest, so it's not moving at all at that point, so it can't be moving to the left. Okay, and the last one here is the particle speeding up or slowing down at t equals 2. So we'll check the signs of the velocity and the acceleration. Plugging v2 into the velocity function, we get 3. So that's just a positive. If I plug a 2, actually I shouldn't assert that this is equal. Now, let me show you something about, we've got to be careful not to ever write something that isn't true. So maybe below this, I can just indicate that as a plus. If I plug a 2, I'm going to do this for 2 then. So this is the velocity at 2. So this is a positive number. 2 minus 1 is a positive number. And 2 minus 3 is a negative number. So I can just use that as evidence to say why that is less than 0. And then for the acceleration at 2, I'm using this right here. I'm just going to actually compute it. 6 times 2 minus 12. That's interesting. It's equal to 0, right? Which means that if the acceleration is 0, that means the velocity is not changing at all. So it's neither speeding up nor slowing down. So I think we'll say this, because a of 2 is 0, the velocity is not changing. Therefore, the particle is neither speeding up nor slowing down. At t equals 2. All right, another case that can come up. All right, let's look at another example. Lots of different ways to ask questions about velocities and acceleration. So the velocity of a particle moving along the x-axis is modeled by a differentiable function v, where the position x is in meters and the time t is measured in seconds. Selected values of the velocity in meters per second are given in the table. Estimate the acceleration of the particle at t is 36 seconds. Okay, pause the video, give this another try. All right, so what I'm thinking is we're trying to estimate the acceleration. The acceleration at time 36 is approximately equal, well, it's equal to the velocity derivative at 36. So let me be really precise with the language here. The acceleration at 36 is exactly equal to the derivative of the velocity at 36. But since I have no function for that directly, I can't compute the derivative. So I can say it is approximately equal to the average rate of change near 36. And since 36 is here, we can find the average rate of change in this region here. So I'm going to say it's the velocity at 40 minus the velocity at 32 divided by 7 minus -4. Oops, wait, I have the wrong things here. This is 40 minus velocity at 32 over 40 minus 32. Now, I have to actually plug numbers in here. So the velocity at 40 is the 7 number, minus the velocity at 32 is -4. And then this is 40 minus 32. Okay, we do not have to simplify this number, so I would not do that. But we do have to put units on here. So the derivative of this will be meters per second per second. So meters per second, because we took another derivative, so it's the slope of that per second. Which if you do simplify, it turns out to be 3/2. Meters per second squared is another way to write that. Okay, let's take a look at another one. How many examples do we have here? Oh, just 2 more. If a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is given by a position function. So this problem is giving us position instead of velocity this time. Find the velocity of the ball. Then what is the max height reached by the ball? And what is the velocity of the ball when it's 96 feet above the ground on its way up and on its way down? Okay. All right, so what's happening here is we have the ground. Ball is thrown vertically upward, given by initial velocity. So at time 0, the velocity is 80 feet per second. And so what we can do is, it says upward with a velocity, and that's defined as positive, which means this is the positive s direction. Okay, and so what's going to happen is the ball's going to go up for a while, and then gravity is going to slow it down, and then it's going to turn around and fall back down. Find the velocity. So for part A, we're simply taking the derivative. Velocity is the derivative of the position. So that is 80 minus 30t. That's all we need to do for that. For the second part, what is the maximum height? Okay, so what would happen, what's unique about this point here is that the velocity is positive on the way up because we're going in the direction of positive motion here, and they said that s is given this. So these are all positive numbers for positive time, right? We can start positive. Right, and then on the way down, the velocity will be in the negative direction. What's unique about this point at the max height is the velocity is 0. Right? Just for an instant, the ball will be at rest. So maybe I would say that the max height occurs when the velocity is equal to 0. Right? So this function I just found, 80 minus 30t, has to be set equal to 0. That means 30t has to be equal to 80. T is 8/3. And the units for that would be seconds. Right? Now that's not what the problem is asking. It's asking for the height. So then what we need to do is plug that magic time into this position vector, the position function. So t at 8/3, or sorry, s at 8/3 is 80 times 8/3 minus 15 times 8/3 squared. And you can leave your answer like that. That is the max height. So I'm going to say the max height is, I'm just going to report that number, 80 times 8/3 minus 15 times 8/3 squared. But we have to have units, and units here are in feet. So you can report this as the answer. If you do simplify it, it turns out to be 106.667. So if you do simplify it, you're required to write the number, like if this is on a calculated part, that's accurate to within 3 numbers after the decimal. Okay, and then the next question here says, what is the velocity of the ball when it is 96 feet above the ground on its way up and on its way down? Okay, so the velocity, okay, what is the velocity when it is 96 feet above the ground? So the first thing we have to do is say this occurs when the position is equal to 96. So 80t minus 15t squared would have to equal 96, which means you have to solve this. So that's a quadratic. If we run the non-calculated part of the test, we can solve it with quadratic formula. But presumably this would be on the calculated part of the test, so we can enter it this way. Let me show you how you can solve this equation. What I'm going to do is plug in the left side of this equation as y1. So that is 80t, the position, make sure I'm working in position, 80 times the variable t minus 15 times variable t squared. And then I'm going to put for y2 that the velocity is 96. And I'm going to graph both of these. Now I'm probably going to have to set the window something meaningful. Let's try 0 to 20 for the time. And then let's try 0 and let's see, maybe, let's see, how big is this max height? This is like 240 divided by 3, so that's about 80 minus some stuff. Let's make it 100 and see where we go. And one thing about the graphing is you have to be able to get this on the screen. Right? Yeah, so let's move this up a little bit. The time doesn't need to be as wide. So let's just go 0 to 10, but let's double the height to 200. Okay. So here is the height of the ball going up and going down, and here is the height of 96. And so there are two times, one on the way up and one on the way down when that occurs. So what we can do to solve this equation is use the intersection feature. Second trace, intersect, and then what we'll do is position this in the vicinity of one of the intersections. We have to tell it that this is the first curve, this is the second curve, and that's the guess, and it'll position it right there. So this occurs at 1.82333926. So I'm going to note that, 1.82333926. That t equals 1.82333926 seconds. Yep, and here's another point. And that is the other intersection. So if I go back and do intersection again, and this time position in the vicinity of the other intersection, this is when it's on its way down. First curve, second curve, guess, 3.5099407. 0.5099407, 3.5099407 seconds. So they want us to have the velocity of the ball at those times, so I'm going to have to plug those two times in. So on the way up, the velocity at 1.823926 is equal to, and then we can plug that time into the velocity function that we found here. So again, I could just plug it in. I don't have to write it. I can actually compute it. It's 80 minus 30 times 1.82333926. But if I wanted to, I could go ahead and plug that in. That ends up becoming, let's see, 25. So that is 25 point. Now I'm going to round this 298. And the units would be feet per second of a speed unit. And then on the way down, that happens at the other time, so the velocity at 3.5099407 seconds turns out to be negative 25.298 feet per second. And that makes sense because it's moving in the positive direction on the way up and the exact same speed on the way down. That will happen as long as the system is not losing energy, so this is neglecting things like air resistance. All right. And then one last example here. A particle moves along the x-axis so that its velocity at time t between 0 and 6 is given by a differentiable function v, we're only given the graph of the information here. Determine what time intervals, if any, is the acceleration of the particle negative. All right, so The acceleration of the particle, just thinking of this through, and let's write sequence here, that's equal to the derivative of the velocity. So for the acceleration to be less than 0, that means the derivative of the velocity would have to be negative, right? Now the derivative of, if this is a graph of v, that means the derivative will be negative, where the graph of v is decreasing. The graph of v of t is decreasing. So where does that occur? Well, the graph is decreasing here from 0 to about 1, looks like, and then again from 4 to about 6. I assume we can round those to those values. So I'm going to say, therefore, the acceleration of the particle is negative for, let's see, between 0, I'll use interval notation here, 0 and 1, and 4 and 6. Right? Or, yeah, should we put the, I don't think we should put the influence on here, because this has to be a decreasing behavior, which there's no behavior of that type at the ends of the intervals. So you should either write it this way, I think, or we can use the symbol t here and not include influence. Might want to say seconds though. Oh, but they didn't give units, so never mind, no units. All right, I think that's the last example. Yeah, each of these is a little different, but they do follow certain patterns. Let's just really quickly scan through the things that we were asked here. Very common, to be given a velocity function and then asked to work with acceleration. Take the derivative and answer questions. Things are at rest when the derivative is 0, so when the velocity is 0. Okay? For finding a minimum or maximization, you can do a candidates test on the derivative of that object, right? And speeding up or slowing down, speeding up whenever the signs of the velocity and the acceleration are the same, slowing down if the signs are opposite. Right? If you have to estimate a value for a derivative, just use the average rate of change over the closest interval that you can get to that value. And that would be an estimate of the derivative. The estimate of the acceleration is an estimate of the derivative of the velocity. So you're doing an average rate of change of velocity values. If you have something where you have an object being thrown, the maximum height occurs when the velocity is 0, because the object pauses for a second. It will have positive velocities on the way up and negative velocities on the way down. And then finally, just remember the same things from earlier in the unit, where if you have a graph of a function, you can determine where its derivative is negative by looking at where this function is decreasing. And then this could also be in the context of physics. All right, that should be it for this video.